So let's continue, and before we explain the format of the next instruction, I would like to scroll back here just for a second to clarify that what I tried to do here, of course, this is an opcode like this, so we can write opcode is and so that it's more or less obvious what our description is trying to say in this field. So moving on, move EDI AL, yet another move instruction. Of course, move EDI AL, encoding is this line. Okay, so this is this line that the disassembler given to us, and right away we say opcode is, right, and opcode is 88, but let's verify it in the manual. So yes, 88 is right at the top of the move instruction reference, and we say that opcode, so we can just take the entire line from here. Opcode is 88 with /R, and let's get rid of this and just keep the description of this instruction. Okay, so opcode is 88 followed by something, and that something we need to be able to find right here. R indicates that mode RM byte, so we can copy and paste this, indicates that mode RM byte of the instruction contains both a register operand and RM operand. So basically the entire mode RM byte, all bit fields of this mode RM byte are in use. Okay, so this is mode RM byte. Let's resize this. So /R indicates that mode RM byte of the instruction contains both register operand and a register or memory operand. And right here, this is our memory operand and this is our register operand. So let's get started and find out what it is. So in our case, mode RM byte, right, mode RM byte, we'll just write like this, is 07. It follows the opcode byte, and so which means that of course it's 0000 and then 0111, right? So I guess I can write binary version of 07 without using the calculator. You know that these are the fields of mode RM byte. Just quick jump here: 2 bits, 3 bits, and 3 bits. And so let's take a look at the reg. Let's just say that so here we have the mode RM is 00111, right? So it's this and this, and the reg, all right, so we can write reg over here. Reg field is of course 000. A reg field comes from this table, and 000 is register AL. Why is it not AX or EAX? And the answer is because the opcode description told us that this is 8-bit register. So reg is 00, which means AL. So remember, we have this table for a reg field portion of the mode reg RM byte. This is like part 8 of our slides, so these are the codes, and these are the names of the registers that they could represent in different situations. But we already knew that this is 8-bit because right here the instruction reference told us so. So which means AL. And so what is mode RM? It's 00111. So let's look this up in addressing modes. So we need to locate once again 00111, which is close to the bottom of this list, and it indicates EDI, right? So this is EDI, obviously, exactly what our instruction is doing. So which means right here we can say which means EDI, or I can copy and paste like this, EDI. Which means EDI, that is register EDI contains the address of the 8-bit, right, of the 8-bit operand in memory. Okay, so that's the whole story, that's the whole explanation of what these 2 bytes represent. And you may start wondering, why are we doing this? It's sort of tedious and begins to feel like a little bit unproductive. It's sort of repetitious, and it is making an impression of a bit of an unproductive process or assignment. Is like, why are we doing this? What is the reason for struggling with the manual and all other parts that we use in the presentation? What are we doing? What is the ratio of signal to noise? And the answer is that, well, first of all, I can tell you, I can assure you that what we're doing right now is the lowest possible level of activity that you can attempt in software, given specific platform. Of course, this is Intel x86 platform, and therefore this experience is the lowest level. It cannot get lower, because now you're looking not even at bytes, you're looking at individual bit fields to understand the meaning of what you're doing. And this is where it could come handy. If you're debugging something, okay, if you have a crash, or you could have like a hacker attack, and you have identified memory where, for instance, something got corrupted, something looks very suspicious, or simply some program has crashed, and you don't have access to the original source code, and you still want to find out what is the potential reason why this process has crashed, because you may have done something that caused that situation, and therefore you still want to find out. And oftentimes it is just possible to try to disassemble memory, and when you try disassembling, you actually may not know whether it's a data segment that you're disassembling, and therefore it's very unproductive. It's the data, it's not part of the text segment. Or you could be disassembling the actual instructions, and therefore if you're unsure, all of this information that you can extract out of sequence of bytes, where you just have the crash address and the sequence of bytes, you definitely want to reconstruct this on your own, because your disassembler may try to reconstruct it from this byte and give you some kind of garbage. But you need to be able to identify this as as it is and be able to convince yourself that you're actually using or looking at this instruction that does this. Okay, and likewise you can move on to the next piece and to the next piece, and if you spend a little bit of time and you recover a section of code like this, all of a sudden it gives you this confidence that you did the good job interpreting it, and now you realize that this is actually a loop which happens to be executing, iterating certain number of times, and you begin to formulate the whole story of what is happening, and this gives you a tremendous boost to start your identification of this bug or your network intrusion or something else that caused some kind of drastic situation. So the practicality of it is still very, very high. At the same time, on the theory side, again, I told you that this is the lowest level of activity that you can possibly attempt on any platform. Basically, looking at the instruction bytes and try to understand every single bit or bit fields. Of course, with the help of the manual, which is the official manual, but the manual doesn't do the work for you. You're doing this work. Okay, so that's the reason why we are attempting to kind of go at this level and try to make successful, progress through this challenge.